Yeah, it's really a pleasure to have been invited to give this talk to the Slovenian Med Society. And well, as you said, we know each other since a long time, and I would say that we developed a kind of friendships in these years, and so it's really nice for me to be here for this talk. So I prepared a lot of material, but okay, I will try to stay in more or less 45 minutes, not more than an hour, also because then I will be hungry because and also without liquid in my mouth. Okay, so I'm going to talk about cryosphere in this talk, trying to give some let's say some connections with the atmosphere, of course, because the cryosphere is strictly correlated with what happens above it, so in the atmosphere. I start with a picture which is indeed not related to the Eastern Alps, but it's the Adamel Glacier, which is facing a terrible, huge, terrific melting lately, especially in the last 30 years. You have seen this picture from the late 80s, and now the situation is this one. So I made a contrary. I showed you before the present state of the cryosphere here in this glacier, which is the largest, which was and still is the largest glacier in Italy, which is some 10 kilometers square of surface. And the problem is that at the moment, the Adamel Glacier is lying below the equilibrium line altitude. So it's completely in the ablation zone, and is facing meters and meters of melting every year. I mean, in surface topography. But let's see first what the glacier is, and which are one of the most important characteristics of a glacier. So I synthesize here in this easy sketch, in this simple sketch, a mountain and the glacier in 2D. So during winter, the glacier is completely covered in snow, or should be completely covered in snow. Then in summer, part of the snow melts, and this happens especially in the ablation zone, which is the lower part of the glacier, where of course is warmer. In most, if not all, the ablation zone, also the ice melts during the summer. So we lose the snow that felt during the winter, but also the old ice coming from the upper part of the glacier. In fact, the glacier is flowing in this way. You see, in following this arrow, and the border between the part of the glacier which stay with some snow remnant from the last winter, and the part which is completely outcropping to the atmosphere, this border is called the equilibrium line altitude. The equilibrium line altitude is basically the border between the old snow and the old ice. Old snow meaning the snow of the last winter. And you can see in this picture, this is the Ortles group in the Central Alps. Here in the upper left, you have the Forni Glacier, which was the largest glacier in Italy, now is facing a very rapid shrinking and melting. And basically, if we fly over a glacier during the late summer, early autumn, we can trace, like I did in this picture, the equilibrium line altitude. So the whitish area is the accumulation one, and the red, more black area here is representing the ablation zone. Oh, the ELA is directly correlated, strictly correlated to the climate, and mainly depends from the temperature, average temperature, mean annual air temperature, and mean annual precipitation, or summer temperature, better, and mean annual precipitation. So in this plot, you can see the blue zone, which represents the climate conditions able to trigger the existence of a glacier. The red zone is that one of the permafrost, which is normally characterized by a cold climate, but also dry. And the green one is the periglacial zone, where you don't have glaciers, you don't have permafrost, but it's still a quite cold area. So if you would like to put the Triglav Glacier in this graph, the Triglav Glacier is just lying very close to the border between glaciation and a periglacial zone and the permafrost. So it's just there in the middle. Of course, in the past, when the climate was colder and precipitation was more or less the same as now, Triglav was completely inside the blue area. In fact, in the past, there was a huge glacier. So how it works, or how the equilibrium line altitude is correlated to the climate. Okay, let's make it simple. So we have here 3 different mountains and 3 different kind of glaciers: a valley glacier, which is flowing down valley, a mountain glaciers, and a mountain small glacier, which is, it's just a small area, like could be, for instance, I don't know. Well, try to think to an example. So the ELA, as you can see here, is dividing, as we saw, the white area, the accumulation area, from the ablation area. So if the climate change, as it is doing now, and for instance, temperature are increasing, like now, the ELA rise. This means that the accumulation area of a glacier becomes smaller, while the ablation area becomes larger. And if this happens rapidly, as it's happening now, at the beginning, you don't see much of an effect. So the glaciers stay more or less at the same size, but they are immediately not in the climate which is good for them. So they are not in equilibrium with the climate. So in this situation, these glaciers are not in equilibrium anymore with the climate. So what happens? The small glacier, where the equilibrium line altitude is above the highest peak, just disappear, and all the other glaciers shrink. Generally, the valley glacier, as it's happening, for instance, in the Pasterze, close to the Grossglockner Gloop, the valley part of the glacier becomes a lake, as it's happening now, and all the other parts just become smaller. So let's say, what does it mean, better the ELA? We saw that the ELA divide the accumulation area from the ablation area. In an healthy glacier, at the end of the season in summer, 67% of the glaciers should be in the accumulation area. So 60% of the glacier should have still some residual winter snow of the last winter. And only the 33% of the glacier should be in the ablation area. So only in 33% of the glacier, the ice might outcrop. This is called the accumulation area ratio. And of course, it should be 0.67 in a glacier which is in equilibrium with the climate. But now in the Alps, we are facing at the end of the season glaciers that appear like this. This one is again the Adamel Glacier, the largest in Italy, 10 kilometers square. At the end of the season, you see that all the ice is outcropping, and only few parts of the glacier are white with some residual snow of the last winter. This was taken on 23rd of September 2018, but every year you can see the same picture more or less. So in this case, the accumulation error ratio is 10%. So only 10% of the glacier is still covered in snow. This means this glacier is not in equilibrium. So starting from this assumption, we worked recently on a project called Change, in which we reconstructed 200 years of climate records, precipitation and temperature in the Alps, starting from 1901 and modeling the climate until 2100. So we worked in all the Alps, and this was made to reconstruct and model the environmental ELA, which is, I tell you again, is strictly correlated to temperature and precipitation. And doing this, we can see how at present condition, the ELA in the Alps is more or less around 3,200 meters, and it was below 3,000 meters at the beginning of the 20th century. So using different scenario, mostly the three main scenarios that we have, the RCP 2.6, 4.5, and 8.5, we model what could happen in the future, in the near future, and we see that in the best case scenario, we still have a small rise in the ELA at the end of the century, but if in the other two scenarios, especially in the worst one, we could face a terrific increase of the ELA at around 4,000 meters at the end of the century, and average in the last 30 years around 3,900 meters. So this means that in the worst case scenario, 92% of all the glacier in the Alps will be gone. So these are the real facts related to the link that there is between global warming and the response of the cryosphere. But even in the best case scenario, which is the RCP 2.6, we are going to lose 70% of all the glaciers in the Alps. And let's remember that in the Alps we have something like around 4,000 glaciers, counting Italy, France, Switzerland, Austria, and Slovenia. So let's make a step back in the climate, and let's go to the end of the last glacial maximum, something like between 24 and 18,000 years ago. And we can see which is the best knowledge so far about climate change. To be honest, lately a new paper came out which slightly changed this view, but it's still in debate. This plot anyway comes from different proxies, and it's a global temperature variation related to 1950 as base. So we have many things that happened in this time span of 24,000 years. The huge Alpine deglaciation followed by the small cold event of Young Adrias. Then in this phase of rapid, you know, in the paleoclimate, rapid means several thousand years, not a few decades, as it's happening now. We have probably the formation of all the alpine rock glaciers present in the Alps, which are thousands and thousands and thousands, much more than glaciers. Then we have the Holocene in blue, and the neoglacial, the so-called neoglacial, starting more or less 6,000 years before present. And if you remember some years ago in the 90s, when they found the Ötzi, the Similaun man in the Ötztaler Alpe, well, Ötzi died more or less here at the beginning of the neoglacial. Then we have the Middle Age optimum during more or less here, and we have this on a global temperature, this small rise in temperature, which is really some few tenths of degree. And then we have the Little Ice Age. But the Little Ice Age is more and more seen not anymore like a cold event, which is a cold event, but it's basically the end of this long-term trend of cooling, of global cooling, started more or less 6,000 years ago. Then this is what's happening now, the rapid increase in temperature that we are facing lately. So let's have a look at what this rapid increase in temperature means in the Eastern Alps. Here, well, I guess you well know what this means, because you have one of the highest observatory of the Alps still in work, which is the Creda-Rizza Observatory. Here you can see the record of temperature reconstructed and then measured at 2,200 meters in the Canine group. And of course, sorry, this slide is in Italian, but it's really understandable what this means in terms of climate change, because often when you speak to the people, when I have some conference or some talks with people that are not professional meteorologists or scientists or whatever, they ask to me, what, okay, if we will have just 1 degree of temperature more, so what is this, 10 degrees instead of 9, or 15 instead of 14? So this is not as much as we shouldn't worry for just 1 degree. But the problem is that we have to see a rise in temperature of 1 degree or even more in this perspective, in this way. So this is the right way to see what this means. So we are facing much more warm days and much more extremely warm days than in the past, and much less cold days, and more or less the disappearance of very cold extreme days. Then there is also the change in the variance, but let's not complicate too much for this talk. So let's jump quickly to the cryosphere of the Eastern Alps. I will talk briefly about glaciers, then ice in caves, and rock glaciers. So these are my topics. I'm used to work as close to home study area, because as Tanya said before, I was lucky to visit very far places like Antarctica and to work there, and it was really nice, and also especially from the scientific point of view, but also because I saw such huge places, and I feel really lucky for this. But very close to home, we have just an amazing area, which is represented by the Julian Alps and the Karst, the Dinaric Alps, and all the Eastern Alps, very close to the sea, with a lot of different situation. First of all, okay, this is our weather station of the Alpine Adriatic Meteorological Society. We built it in 2012, so in 2022 it will be the first 10 years of measuring. And well, we are facing time to time some problems due to snow in Canine, as you well know. So basically, you can see this is the top of the weather station, and this was the top in April 2014. So we had some damages. You can see also here some problems that some cables are not anymore attached. But nevertheless, the best way to observe the weather and to record temperature and everything, all the meteorological parameter is what's happening actually at the Cretarizza Observatory. In Italy, we don't have an observatory like Cretarizza, and I really envy you as Slovenian, but also Austria has a good high elevated observatory. Now this is something that is missing in Italy. There was in the past. Now we just have automatic weather stations that time to time, break, and we lose data on high elevation, which is one of the main problems in also modeling both weather and climate change at high altitude, because the number of weather stations is not as high as it should be to have a proper material for modeling and for understanding the evolution of climate and weather in high altitude in the mountains. Okay, let's go very quickly. You all know that this area is the wettest in the Alps, more than 2,600 millimeters, but we know that in Canine we have more than 3,000 millimeters per year. And also a lot of snow, 7.2 meters, the 30 years long average at 1,800 meters at the Gilberti Hat. So here the Alpine Precipitation Map, two spots, one in the Northwest Alps, and this is the Julian Alps, and then the Adriatic Alps as well. Mainly because of stow effects coming from the southerly winds in the south and northwesterlies in the northern side of the Alps. So in this area, we have first of all, the canonic glaciers, which are the Montasio, the Canine, and the Triglav. But actually, in a work that I did a few years ago, in between 2011, more or less, and 2016, we found much more ice body than it was supposed before. And actually, we were able to make a kind of inventory of Julian Alps between Italy and Slovenia. And the number is 2023. We can see some examples here. Many of them are characterized by these two steps, let's say, these two of moraines. One related to the 1920 advanced phase, and one which is the Little Ice Age maximum. So these are the most visible kind of moraines. And inside of these moraines, you have the present ice patch or very small glaciers. Actually, the real only glacier that we have in the Eastern Alps, in the Julian Alps, is the Montasio Glacier, which is the only one which is flowing with crevasses and so on. In Canine, for instance, or other glacial body, we don't have any more crevasses and all these features that are needed to characterize an ice patch or a glacial body as a glacier. Mostly they are characterized by things like this: proneval moraine or a pushed moraine or a proneval rampart or a proper moraine, as this one in the Karnitsa Valley. Again, with two kind of moraines set one over the other, likely due to the 1920 advance. So what we did, we map all the cryosphere of the Julian Alps. Here you can see the Montalzio Glacier. These are the Canine glaciers. This is the Triglav and the others. And so this is the present situation, or present, let's say, in 2012. But from 2012 up to now, more or less nothing changed in the Julian Alps, and we will see later why. But anyway, from the Little Ice Age peak, we lost some kind of 83% of glacier area and 96% in volume. So it's pretty much. So we reconstructed also the thickness of all the glaciers, and we can see that in some places during the Little Ice Age, likely Canine Glacier was 90 meters thick, and also the Triglav Glacier was very close to this thickness. So okay, I guess that this view you know very well this view, and I just made in you know some sadness. Unfortunately, this is the present more or less situation. Same story for the Canine. This is in the late 90s, and this was the situation in 2020. So most of the ice mass disappeared, and we just have a few ice patches which remain. This is a 3D reconstruction of taking the picture of 1954, made during a military flight, American military flight in 1954. And now this is the present. Sorry, this is the present situation, which in which you can see the frontal moraine of the Little Ice Age and the trimline dividing the rock falls. Sorry, not the rock falls. The cliff more darker and dirty when where the glacier never reached during the Holocene, and this different color, which is the real color of Dachstein limestone, meaning that this was covering ice and snow more or less during all the Holocene, for sure. So in a recent paper, which we just tried to understand which were the so how the glacial evolution in the Canine group was correlated with some climate proxies, with some climate indices. So we found, so here we have the record of precipitation from 1920 to the present. Here temperatures from 1851 to the present, and we can see the huge rise in temperature in the last 30 years. And then in red, we have the evolution of the glacier front, the glacier terminus in the Canine area, and in blue, the Atlantic multidecadal oscillation. So in the long term, the AMOC index seems to be in phase with change in the glacial length of Canine Glacier. And same evidence was found also for the Swiss Alps by Huss et al. More or less 15 years ago. So apparently, the glacial evolution in terms of size is correlated with the AMOC. So here you can see the Italian sector of the Julian Alps. This is the Montasio Glacier, which is also the lowermost glacier in the Italian Alps. Its front is about 1,900 meters, which is really low for the Alpine average. And this is what remains of the Eastern Canine Glacier. So thanks to several LiDAR flights performed in 2006, between 2006 and 2018, we just calculated the topographic difference of these ice bodies. As you can see now, the Montasio Glacier is the largest one, much larger than what remains from the larger Canine Glacier during the Little Ice Age. But we focused mainly on the Eastern Canine, which is what we are monitoring year by year, performing mass balance measurements. And so we were able to reconstruct a long time, well, not as long as other glaciers in the Alps, but pretty long time series of mass balance. So a cumulative mass balance 2006, 2011, and then an annual mass balance up to 2018 in this work, but of course is updated until 2021, and we will of course perform also in the future, luckily. So what comes from such monitoring is that we had, of course, seasons with negative mass balance, but we also have seasons with quite a huge mass balance. But at the end, from 2006 up to 2018, mass balance of the Eastern Canine Glacier is positive, which is something unbelievable for the rest of the Alps. So in 12 years, the Canine Glacier was able to gain something like 2.6 meters of water equivalent, which is completely disconnected with what is happening in the rest of the Alps. You can see in this plot, on average, the Alps are losing lost more or less more than 10 meters of water equivalent, while the Julian Alps, and the Canine in this case, gained mass. So this is really strange. So we try to understand why this is happening, and trying to analyze weather and climate of the last 15 years, or let's say last 30 years, and we found what we expected, basically. So the average summer temperature, which is this plot, of course, increased, and we know this. Winter precipitation in this plot didn't change as much, didn't change so much, but we see already here something strange. These peaks that are quite frequent in the last 15, 20 years. Then in this plot, we see the length of the ablation season, which is increasing. This means that more ice and snow generally melts during the summer, which is something that we were expecting. But we saw something which started to be weird. The ELA, the equilibrium line altitude, increased up to early 2000 and then decreased and then more or less stabilized. So up to the early 2000, up to now, we are seeing a kind of stabilization of the ELA, or even a rather small drop in the ELA. And why this happened? This happened because we had some extreme events of snow lately in some season. The 2013-2014 season, 2008, 2009, also last year, 2020, 2021 was pretty snowy, especially at the end of the season, especially in spring. Here is missing. All these chaos that you see down here represent all the other seasons in the past. So basically, the stabilization of the equilibrium line altitude in the Julian Alps is mainly motivated by an increase of severe weather events during the winter. So extreme snow accumulation that were able to influence the ablation, not only in that season, but even for more than one season, maybe 2 or 3 seasons, like happened in 2009, because the snow that fell in 2009, 8-9, influenced the glacier fate for at least 3 or 4 years, because all that snow didn't melt for several summers. So looking at the literature, there is pretty a lot of work related to something, let's say, new, which is the quasi-resonant amplification and the influence of global warming, or let's say the anthropogenic climate change, on planetary wave associated to the occurrence of extreme weather events. So basically what is happening apparently is that Arctic amplification well, let's make a step back. Rossby waves seem to act differently from the past, and this is probably linked to the Arctic amplification. So Rossby wave, which in the recent past, was acting like the solid line, now act differently. So they are more meandering, and for this reason they are slower to move west to east, triggered by the westerlies. So these two effects, the latitudinal deformation of Rossby waves and the slowdown of the Rossby waves, produce an increasing likelihood of extreme events, but extreme events that are warmer and hotter generally. So more intense precipitation, extreme heat waves, especially during the summer, stronger winds and storms, and also dry periods. But if they occur during the winter, they can lead to extreme precipitation event in form of snow. And analyzing what happened in the past, especially in some very well-known winter like 2008-9 and 2013-14, which were very snowy, but also in dry winters like 7-8 or 11-12, we found what we were searching for, and we found that there was this correlation with this. So this is in the global perspective, in the global view. More locally, we observed another case, which is the surface temperature, the sea surface temperature in the Northern Adriatic. We are lucky enough to have quite a long series, quite a long data record of these temperatures. And this is a recent work published in 2019 with a colleague of the Marine Science Institute. And so basically, we observed that the sea surface temperature rised by about 1.3 degrees in the last 100 years. So this is more or less the trend. What is important, why this is important? Because the sea surface temperature influence the low-level jet flowing like Hugo, like southerly winds during precipitation events. So from a dynamical point of view, the low-level jet behaves in two different ways. And this depends of the velocity of the wind impacting the chain, the mountain chain. How much high is the mountain chain, and depends on Brunt-Weisseler equation frequency, which strictly represent the stability of the air mass. So in these two cases, we saw that if we have a warmer sea surface temperature in the Adriatic, this case, so the flow over case with a Froude number high, we have strong vertical wind velocity, higher precipitation of the first reliefs. And in this case, so we have, during the winter, we can have a lot of snow, extreme snow events in the Alps. So basically, we saw that, or we hypothesized that global warming is in a way influencing how our small glacial remnants in these small alpine sectors, in these who cares sectors of the Alps in a global perspective, both globally and locally, with all these things that I just mentioned. But of course, if you are interested in this work, you can read it in Atmosphere, in the journal Atmosphere, and it was published in 2021, so it's very, very recent. So this is all related to glaciers. So let's make a step back. Do you remember at the beginning of this talk, I was talking about the accumulation area ratio, which is now in the largest glacier in the Alps around 0.10, 0.20, which means that the glaciers are not anymore in equilibrium. So if in this case we have an accumulation area ratio which is less than 0.10, so less than 10%, and we also have a large debris supply, so small or big debris, means rocks, gravel, and things that just fall on the glacier. These objects become something different. So they are not anymore glaciers, but they are rock glacier, where the ratio between how much rocks and debris are present in the glacier is in favor of the debris. So we have more debris than in these objects. In this case, the ELA is surely above the highest peak of this small mountain here, and the debris supply, as you can see from this cliff, is very high. But in this case, where is the ELA? Where is the accumulation? How can we calculate the accumulation area ratio? We cannot, because we don't have an accumulation area ratio. But still, we have this object, which is a rock glacier, which is flowing down, and inside this object, we have a lot of ice. So here there was a glacier, or just this object just formed from this talus made of debris, and that's it. So the modus or formation of this kind of objects is still in debate in the global community studying these kind of things. But by definition, a rock glacier is a lobate or tongue-shaped body of frozen debris with characterized by ice in form of lenses of ice, but also interstitial ice inside all these debris, which is in a way linking all the debris and moving all together this debris like a lava flow, more or less. Rock glaciers are are in great number in the Alps and in all the mountains in the world. So, do you remember absence of debris, a glacier accumulation area ratio above 60%? We have a glacier which is, we have an earthy glacier. Then we have debris covered glacier, which is still a glacier with the debris just above. And in this case, the supraglacial debris protect the glacier from the solar radiation, and accumulation area ratio could be also small, and still the glacier can be great, can be large. But then when the debris, which is this gray line, is covering all the glacier and also inside the glacier, because this debris coming from the cliff is mixing all the ice and the snow and the glacier and the ice that we have there. So the ELA is significantly lower. Sorry, the ELA is significantly higher than the highest peak of the mountain, and the accumulation area ratio is significantly lower than 10%. So this was just a brief introduction to talk about how many of these objects we can find in the Eastern Alps between Friuli, Venezia Giulia, Italy, and Slovenia. We don't have many of them. The number is between 50 and 60, and most of them are located in the Carnic and Alps. In the Carnic Alps, in this corner between the Carnic Alps and the Friulian Dolomites. But there are someone also in Slovenia. They are made mostly by limestone rocks, of course, and they are very often covered by vegetation, by wood, and because the climate is not anymore supporting active forms of this kind. Here we can see some 3D reconstruction of some rock glaciers. This is in the Friulian Dolomites. This valley is the Valvino Valley. It's a very nice area, very wild as well. And this one, which is completely covered by a forest of pine and larch, is a relic glacier. But what it's interesting that we were measuring the temperature of the spring of this rock glacier. It's a permanent spring, and you can see at the end of the season the temperature is 2.5, which is very low. Another 3D reconstruction of this area. So one rock glacier here, one rock glacier here covered in vegetation. This is the LiDAR, which makes it easier to see to visualize the rock glacier. In this case, it's very nice. You can see this huge rock glacier overlapped by a younger rock glacier coming from this cliff. We started to study another rock glacier in the Carnic Alps, in the Casera Razzo area between Friuli and Veneto. Here you can see, again, with the LiDAR, the nice structure of these kind of things. We perform many things, geological, geomorphological maps, and so on, pictures, 3D, and whatever. But mostly, we started to measure some holes in the front, at the front of the rock glacier, in this way. So measuring the air that was flowing outside from the ground, and we found a lot of interesting things. So this is just the climate of the area. Sorry, the blue line is the average temperature in this area. So it's not so cold. You can see the average annual temperature is about 3 and 5 degrees Celsius. It's following the same trend of temperature that we are recording in the Canine group. But this is the situation of this air coming, the temperature of the air coming from those holes in the ground at the front of the rock glacier. You can see that in winter, you go down -10, -15, and so on. But in 2017-18, when the snow thickness was really high, more than 2 meters for a long time, the temperature didn't drop so much because the snow was insulating the ground from the cold air to penetrate in the ground and in the soil. This blue line is the temperature at the soil surface, and for this reason, it is able to reach more than 15 degrees during the summer. So on average, you can see that the monthly values of these stations, these sites, these holes, are more or less in phase. So few degrees above zero during the summer, July, August, September, then below zero. And this is the air coming from this hole. So this means that something strange was happening inside the ground. The ground is like this. You can see normal mountain view with dwarf pine, larches, talus, and so on. So this is the area. This is the old rock glacier. I'm showing you with the mouse. So we performed geophysical measurements in the front. This is the front of the rock glacier. Here in this part, there are those holes that I showed before, and where we were measuring the temperature. We performed a geoelectrical tomography, and actually we found what we were searching for. These blue areas represent the presence of ice. So we have a lot of ice in this object, which is located at 1,700 meters. This is the base of the front here where the spring occurred. Here we have more or less those holes that I was talking about a few slides before. So these holes told us the truth. So the air was so cold because we had ice, we have still ice in the ground. Here, well, the picture is not perfect, but at the base of the rock glacier, we have a spring. This is fresh water coming from the base of the rock glacier. This is the location of the spring. This is ice, melting ice during the summer. You can see better here the water coming from the front of the rock glacier, and during the summer, well, early summer mostly, forming a temporary lake at the base of this area. There is also something nice more down in the valley, which is this relief, and this is a glacial moraine. These are glacial moraines in this area. This flat area is an old war airport, World War II airport built in this area, but the moraine is still intact in here. So this means we had a larger glacier, then the glacier shrunk, retreated, and a rock glacier formed, and now we have this relict form, but still preserving some ice inside. And then in this area we have these two nice permanent lakes. But how it works? It works such kind of object rock glacier. In this case, in the Casera Razzo area. So with blue lines, with blue arrows, you can see what's happening actually during the winter. So the cold air inside is, or better, the warmer air inside the rock glacier, because outside is very cold during the winter, just flow up, creating a low pressure inside the void of the debris. And so this low pressure is inspiring inside the cold air for outside. So the ground cools down in these sectors, mostly in the front and in the lower sector of the talus slope. During the summer, the air circulation is inverted because colder air, which is also denser inside the ground, just flows outside from the front. And we were measuring in those holes in the front of the rock glacier, this cold temperature which were flowing down in this part, and warmer air is coming from the talus, the higher part of the talus, for the same reason, because this flowing of dense and cold air outside the rock glacier formed a depression inside, which is sucking warmer air outside. What is interesting, why this is interesting to study these kind of things, because from the Alpine Permafrost Index, this is the rock glacier that we were studying, we were not supposed to find any ice, any permafrost in the ground, but we found it some 700-800 meters lower than the Alpine Permafrost Index tells us. So this is important because in terms of water availability in mountain areas is probably much higher than previously supposed, starting from indices like the Alpine Permafrost Index and so on. So to be this one is the largest rock glacier in the area, almost 1 kilometer long, and is this one. This is the 3D of this glacier. Okay, last part of this talk. I think I have just 10 minutes, so I will be just 10 minutes late. I hope that is interesting you what you are listening to. And so the last part of the cryosphere is buried like in the rock glacier, but in a way it's easier to reach because it's the ice in the caves. So as a speleologist, I can cave. So this is an easy cave, but there is also ice in more difficult caves in the mountains. And what we are doing since a decade now is measuring several things in these kind of caves. First, the temperature of the air and of the rock, and sometimes also temperature of the ice. So we found we built a microclimatology of some of these caves. Here you can see one of the most studied caves in the Alps so far from this point of view, which is the Leopard Ice Cave. This cave, now we have an 11 years long record without any stop of temperature in the rock, in the air, which is quite a huge data set. So cave temperature is about -1.4 with extremes between -12 and +3, which are value very close to Tarnowski Ghost, Ledenik caves that you have in Slovenia. So how actually work these environments? More or less by using the same chimney effect that I was explaining for this relic rock glacier. So during the winter, warm air is flowing outside from the chimneys, creating a depression, a low pressure inside the cave, which is sucking colder air from outside. So during the spring, the flux is cyclically inverted, depending on the temperature that we have inside and that you have outside. So basically, this is the season where you have the most extensive presence of ice, because also stalagmites and stalactites forms form in the cave, because the snow melting is starting outside, so the water is dripping inside the cave and freezes as soon as it reaches the cave environment. Then during the summer, cold air, denser air flowing outside the lower entrances, and warmer air is sucked from the upper entrances. And fall is the worse season for an ice cave because temperature is close or above zero. So in this phase, the ice generally reaches the lowest size in terms of volume and extension. What we are now doing for monitoring ice in the caves is that it's not easy to perform a mass balance monitoring in caves as it's easier outside, because outside huge glaciers, even Greenland or Antarctica or larger glaciers, are easy to measure even with satellites, with flights, and so on. We have a lot of instruments for doing this. But actually, for measuring an ice cave mass balance, you have to go inside the cave. There are no other way to do it at the moment. You cannot do with a satellite or other kind of automatic procedure. So we are performing a lot of study and applications in this. Okay, I'm not going to talk about paleoclimate and things that you can find inside the ice, because otherwise we should do a talk just for ice caves. But let's concentrate about mass balance, what is happening now. So we saw, for instance, in this cave, that starting from 2014, something changed, and the surface topography started to decrease very rapidly, as you can see in this graph. And this happens between July 2014 and November 2014. The ice detached from the walls, and this caused positive feedback due to increased air circulation between ice and the rock, which is actually melting faster all the structure. But so we had a look to what happened on early November 2014 in that area. And we found that in the Julian Alps, especially in the Canine sectors, something like 900 millimeters of rain was falling in a matter of a week. And it was pretty warm at 2,300 meters because the temperature was between 2 and 4 degrees. So a lot of water came inside the cave, and this water produced a domino effect, increasing the temperature of the rock, of the ice, of the air, and an extreme and rapid melt occurred in this cave. Starting from that point, the cave is not anymore in permafrost condition. I mean, the rock is not anymore constantly below zero. And during the summer, it warms above zero. And this is causing a feedback, positive feedback. In summer and fall, the melting during summer and fall, the melting is much, much stronger than in the past. So to measure, to record the mass balance calculations, we are using a structure from motion flow and multi-view stereo view, using a lot of free software that are available in the market. And this is actually one of the best way to quantify exactly or very precisely volume modification of such deposits, underground deposits. So we are playing, we are enjoying with this kind of nice plots that we are able to produce, and basically by using photogrammetry, which is an approach useful also for the external cryosphere, but very, very useful for the underground cryosphere. So for instance, we found huge drops in volumes. One cave lost something like more or less 50% of its estimated ice volume from 2012 up to now. So even the underground cryosphere is facing a rapid decrease, a rapid melting. So I like to end this talk with something that maybe not all are aware of. Why I'm showing this old picture of this old lady, because this is Eunice Newton-Foote, an old scientist. Well, all in time, she was not much old here, apparently. She was pretty young. And sorry, this is in Italian, but she was able to experimentally demonstrate for the first time the greenhouse gas effect. The problem is that, so she published this work, Circumstances Affecting the Heat of the Sun's Rays, in 1856. The problem is that, unfortunately, in that period, in that historical period in the US, she was a woman. And for tens of years, John Tyndall took, let's say, her research, and in the books is written that John Tyndall was the first physician to found the experimental demonstration of greenhouse gases. But this is actually not true. So we have to remember Eunice Newton-Foote as the first scientist. Then, of course, we all know the Svante Arrhenius Nobel Prize for Chemistry in 1903 published the historical paper on science, which at that time was Journal of Science, on the influence of carbonic acid in the air upon the temperature of the ground. But this is a more recent story.